Okay, so in today's video, I'm going to introduce the total sum of squares. So we're going to start with some indexes and some x values. The x values in this will just happen to match the index values, but that won't always be the case. So x1, 2, 3, 4, 5. And then y's will be 2 and, let's see, I wrote this down ahead of time. 3, 5, and 4, and 6. Now I'm not going to go through how to calculate the line, so the regression line for this again. You can see my some of my other videos for that. I'm just going to give you the regression line, and it would be good practice for you to make sure you can do that, and then just make sure that you can calculate this line out of this data. That being said, total sum of squares. So we have this general form for it that the total sum of squares is comprised of the residual sum of squares plus the estimated sum of squares. These two terms we're going to talk about more in detail next time. Suffice it to say, let's start with just total sum of squares. That's going to equal the summation of the difference between the observed y values and the mean squared. So each y value minus its mean, each of those terms squared, and then all of those summed. What this is telling us is, or showing us, is just the total, essentially just variation of our y values, and so it's basically just saying, hey, this is how much our y values are spreading out, and so the compositions, residual of some squares and estimated sum of squares, the reasoning behind that. So I'm going to do a little preview of that, just a kind of a quick treatment of it. Suppose, so each one of these is points. So this would be observation 1, the x value would be 1, and the actual y value would be 2. This is observation 2, the x value is 2, and the y value is 3. So we've got this value 1, and then value 2, then we have some line of best fit, and it doesn't quite hit that point, but that's our first point. And then we have value 2, and that hits value 3. And again, it's kind of moving with the line, but it's not quite perhaps on the line. And part of the reason for that is some of our data points might actually end up around the line of best fit, but not on it. And so the idea behind this is we want a line of best fit, and so we measure it in two ways. So the estimated sum of squares will tell us basically all of the variation in the total sum of squares. So all of this movement in y, which is what TSS is measuring. Estimated sum of squares tells us that's how much could be explained by the movement in our x variation. So that's x is impacting this to this extent. Whereas residual of some squares is a little different. The residual of some squares is, and I erased that prematurely, all of those, and I'm sorry, I'm going to actually add that back. So we have these lines. It's all of the distances, the sum of all of these distances squared off of the line. And so it's basically saying, okay, the line isn't actually hitting each point, and each point has some distance away from the line, and so there is motion off of the line such that not all of our total variation in these y values is explained by our variation in our x values, and so that's what the residual is capturing. We square all of these terms too, because otherwise, I like using the residual sum of squares example. I have some values that are below the line and some that are above. If I have a value that's, say, 2, just a value of 2 below the line of where we predict, and then I have a value of 2 above the line, those values would cancel out because I'd have essentially a negative 2 and a positive 2. So if I want to account for variation, but I don't want negatives to count against me, making the variation seem smaller, that's why I square it. So I get this magnitude. We get the sense of oh no, in fact, this is capturing at least the entire magnitude of variation because our negative values are not detracting from our positive values. So that's the primary takeaway from that. Now, With this, we're just going to do a quick example, calculating our total sum of squares. So first thing we're going to need is the mean of y. So that's going to be, we have 2 plus 3 up here. That equals 5. And then we have plus 5. So that equals 10. And then we have 4 plus 6. And that equals 10. And 10 plus 10 equals 20. So that's the total sum here. And then our observations, our n, is going to be 5. So divide by number of observations. In this case, divide by 5. And that's going to equal 4, which equals y bar. That is our mean. So once we have our mean, then we can go through and just belt these out, calculating these. So first things first, our first observation, 2 minus 4, that's going to be squared, plus, then we have 3 minus 4, that's going to be squared. Then we have 5 minus 4, that's going to be squared. That's our third observation. Plus 4 minus 4, doesn't matter to square that or not because that's going to equal 0, but it will be squared, and then 0 squared equals 0. And then plus 6 minus 4 squared. And then we can calculate these out. So this is negative 2 squared, which equals 4. This is negative 1 squared, which equals 1. This is 1 squared, which equals 1. And finally, at the bottom here, we have 2 squared, which equals 4. We sum all of these terms, including the 0, or if you want to, or you can just ignore it because it's a 0. 4 plus 4 plus 1 plus 1, that's going to yield us 10. So the total sum of squares is equal to 10. Hopefully you found this quick review useful. Next time I will have a bit longer of a treatment dealing with RSS and ESS as we kind of build it towards econometrics. Thank you.